we're starting off taking a look at this question. What is 0 times infinity? Well, on one hand, we know 0 times any number is 0. But on the other hand, we also know that any number times infinity is infinity. And so it seems like it should be 0 or infinity, but as we'll see, we could even actually find that it might even be something in between, just how powerful is this infinity or whatever. It's kind of a weird question and a weird idea. And so in order to deal with this, we're going to be looking at some functions along the way. We're looking at this as called an indeterminate product because we cannot determine what this actually equals. And this is the basic thing that we're going to be working with today, is figuring out how do we solve with an indeterminate product, finding a limit. And our basic strategy when we go to deal with these indeterminate products is to try to make them look like what we can deal with. Remember, we have L'Hopital's rule for the purpose of figuring out how to deal with like 0 over 0 or infinity over infinity. So when I see this situation crop up, I can deal with it basically by turning it into something that looks like L'Hopital's rule. That basically means make it into a fraction. Write this as a rational expression where we have some function over another function. That basically just means writing it as a quotient. And so that's what we're going to do here. We're going to go ahead and write this equation as a quotient and a few others as well to practice this idea. Now the nice thing about writing this one as a quotient is that we actually have kind of this fraction already built into it. Because tangent, well, that's just shorthand for another fraction. What does tangent equal? Tangent is sine over cosine. And so I could rewrite that tangent of x is sine over cosine of x. And that is times x squared. So I can write this whole thing as one big quotient by writing it as sine of x times x squared all over cosine of x. And now I've written it as a quotient. Now if I were trying to find a limit, I now would have something that's actually written as a quotient, which would let me use L'Hopital's rule. Now let's see how we might do it with this one. Now with this problem, we don't have the same inherent fraction. We don't have just shorthand for a fraction already written in here. So we got to do a little bit of work here. So there's a couple different ways you could do it. One way is that you could put the x cubed into the bottom of the fraction. If we did it that way, the e to the x would be on the top. And if I'm going to put the x cubed in the bottom, remember to flip it in the fraction, that means we do a negative exponent. And so it would be e to the x over x to the negative 3. The only problem with this, though, is that when using L'Hopital's rule, we end up taking derivative of the top and derivative of the bottom. And if I do the derivative of the top of this, it's always going to give me e to the x. No matter how many times I do it, I'm going to get e to the x. And on the bottom, my x to the negative 3 would become negative 3x to the negative 4. And then that would become 12x to the negative 5. And notice it's always going to be x to the negative something. We're always going to have some x there. And so while that e to the x over x to the negative 3 works, I'm not a fan of it. The other option that we could go with is putting the x cubed on top. If we do that, we put the e to the x on the bottom, again, by making it a negative exponent. This one, you'll notice, actually, at least the x cubed, when we start taking all those derivatives, that x cubed will go away eventually. And it'll just turn into a number. And that's going to be more helpful. So both of those work as quotients. But in terms of which one are we going to lean toward, we're going to be leaning towards that one when we start using these here in a moment. All right, so then go ahead and write this product then as a quotient. All right, so hopefully you remember what each of these equal, all of our trig functions. Cosecant, that's the one that is 1 over sine. Because, of course, they weren't nice enough to make the cos match up. You know, cosecant goes with regular sine, and cosine goes with just regular secant. And so then if I'm going to then write this as a single quotient, it's going to be cosine of x over sine of x. Now, yes, I could then say that that equals cotangent. However, our goal here was to just write it as a quotient. So I'm actually going to stop there. Because the quotient is what lets me use L'Hopital's rule. If I turn it into cotangent, I couldn't use L'Hopital's rule with that without first turning it back into this. So for the purposes of this problem, yeah, it's fine. But do keep in mind that that is the same as cotangent. All right, now let's take a look. How would we find this as a quotient? And again, in this case, it's not necessarily clear-cut at the start about which way we'd want to write this as a quotient. We got a couple different options. One is we could put the natural log of x on the bottom. If we did that, that would give me the square root of x over the natural log of x to the power of negative 1. If I did it the other way, I could put the natural log of x on the top, and that would give me over, well, rather than writing square root of x to the negative 1, I'm just going to go ahead and write it as x to the negative 1/2. Because, of course, it's the same thing. Both of those are writing it as a quotient. However, let's start thinking ahead. In fact, let's actually make this into a limit problem here. We're going to find the limit as x is approaching 0 here from the right side. Now, before we get rolling on this one, I do want to point out, if I plug 0 in to this and see what is each of these two functions approaching from the right-hand side at 0, notice the square root of x, it's approaching 0 from the right-hand side. The natural log of x, it's approaching negative infinity. And so that's why we have to use some other method here, because this is one of those indeterminate products. All right, so these were the two possibilities for how we could write our quotient. We're going to use one of these to let us solve this out. Now, start thinking ahead. If I'm going to find the derivative of the top and derivative of the bottom, which one of these is going to actually help me get someplace? Well, if need be, actually find out what those derivatives would look like. The one to pay special attention to here, this first one. If I take the derivative of the top there, I end up with x to the negative 1/2 times a half. Okay, that doesn't look too bad. But on the bottom, I'd end up having to use chain rule. So it'd be like negative natural log of x to the negative 2 times the derivative of the natural log, which is 1 over x. Notice that by doing that, I ended up with a result that basically still has a square root in the top. It's just negative square root now. But I still have the natural log in there. Whereas if I take the derivative of this second function, when I go to actually find that derivative, I'm going to be getting rid of natural log. And so that's actually the one I'm going to be using. I'm going to be using this form, this quotient, because it's actually going to let me get rid of the natural log. Now, as you're working on these and learning to use them, you might have to try one and find that it's just getting very unpretty and realize, okay, go try doing it the other way if necessary. All right, so let's go ahead and take this one on though. So we're going to do the limit as x approaches 0 from the right-hand side. And I'm going to rewrite this first just as the natural log of x over x to the negative 1/2. Now I'm going to use L'Hopital's rule. By the way, I can use L'Hopital's rule here because if I plugged in 0 here for top and bottom, notice what would we be getting? It'd actually be like negative infinity over infinity kind of a thing. All right, so derivative of the top, derivative of the bottom. So the derivative of the natural log is just 1 over x. Then that's going to be over the derivative of x to the negative 2, so that's going to be a negative 1/2 x to the negative 3/2. All right, now before I go on, I'm going to go ahead and try to clean this up a little bit just because right now it's kind of scary looking. I know I'm going to end up with some fraction here because there's fractions all over in this thing. So I'm just going to start at the top. That 1 over x, well, that tells me that I put an x into the bottom. The negative 1/2 on the bottom, well, divided by negative 1/2, that's the same as putting a negative 2 on the top. And then the x to the negative 3/2, that negative puts that into the top, so that's x to the 3/2. So then, all that I actually have on the bottom is just this x. Now, you actually can simplify that from here, or you can go ahead and you can take the derivative of the top and derivative of the bottom again. Now, I think simplifying is a bit easier. If I simplified that, it would be the limit as x is approaching 0 from the right of a negative 2 x to the 1/2, and that's it. So basically it's just negative 2 root x. And then we can go ahead and plug in the 0 there and see it's approaching from the right. What is it approaching? Well, that'd be negative 2, and remember that x to the 1/2 is square root of x. Square root is approaching 0 from the right-hand side, so it's 2 times 0, which is 0. Now, some people, though, have a little bit of trouble simplifying the x to the 3/2 over x. Well, basically we're just doing 3/2 minus 1 to get the 1/2, but sometimes that can be troublesome. So, yeah, you could have just kept going here and used L'Hopital's rule for one more iteration, and if you had done that, you get the limit as x approaches 0 from the right-hand side of negative 2 times 3/2 times x to the 1/2 over 1. And again, notice if you then look to see what is x to the 1/2, or the square root of x approaching from the right-hand side, that would be 0, so it's 0 over 1, which is 0. And so either way you did it, you're going to get an answer of 0. All right, so now we're going to take on this limit. Now, first of all, notice that if I actually just try substituting the 0 in for x, for the cotangent, I end up doing 1 over 0, because it's going to be cosine over sine. 1 over 0 basically gives us that infinity condition. And the sine of 0 ends up giving us 0. So this is an infinity times 0. That's why it is one of these indeterminate products, and why we have to use this method of turning it into a quotient. All right, so then let's go ahead and look at turning it into a quotient then. So we're going to go with the limit as x is approaching 0. Fine. But now we want to write this whole thing as a fraction. Cotangent, again, that's cosine over sine. So that's going to be cosine of 2x. And then we know that sine of 6x will end up in the top too. So let's go ahead and do that. Over sine of 2x. So I turned the cotangent of 2x into the cosine of 2x over the sine of 2x. So that's that part right there on the left. Before I go on, got to deal with this question. Can I cancel out the signs? No, we cannot, because they're not the same signs. One is sine of 6x, the other one is sine of 2x, and there is no way to correlate the two. So we really have to deal with it from this format. All right. Now, again, if you tried plugging in just the 0 at this point, you would end up with 0 over 0. So again, that's why we have to use L'Hopital's rule. All right, so let's go ahead and use that rule. That means that we're going to be doing the limit as x approaches 0 of a big fraction. Now in this fraction though, we are going to have to do the derivative of cosine of 2x times sine of 6x. What rule do I need to use in order to find the derivative of that function? Product rule, absolutely. Hopefully you're remembering product rule is original times derivative plus derivative times original. And so in this case, let's go ahead and just start. I'm going to go ahead and start by doing derivative times original first. So I'm going to do the derivative of the cosine of 2x first. Derivative of cosine is negative sine. So that's negative sine of 2x. But notice that since it's a 2x inside and not just an x, I got to use chain rule. So I then multiply that by the derivative of 2x, which is 2. So that is just the derivative of cosine of 2x. So then I have to multiply that by the sine of 6x. Plus, now we flip which one we're taking the derivative of. So in this case, the cosine of 2x is going to stay the same, so it's cosine of 2x, times the derivative of sine of 6x. Derivative of sine, of course, is cosine, so it's going to be cosine of 6x, times the derivative of the inner function, so the derivative of 6x is 6. And then, what's that over? It can be tempting at this point to think, oh, the square of what's below. But that's quotient rule. And the problem, though, is that quotient rule looks a lot like this. In quotient rule, we have a big old fraction with two different pieces on the top, just they're being subtracted instead of added. So it looks a little bit like quotient rule. I bring that up only so you don't get lulled into thinking of it that way. We go and we just take the derivative of the bottom. Remember, we just did derivative of the top, now derivative of the bottom, which is going to be cosine of 2x times 2. Now at this point, I'm going to have to look and see if I plug 0 in for x, does it still give me 0 over 0? Well, I can either clean this up first, or I can just plug it in. And at the moment, I'm feeling kind of lazy about it, don't really feel like doing all the work to clean it up, so I'm just going to start plugging in the 0 and see what that gives me. So I'm going to plug in 0 everywhere x appears. So that's going to be negative, now I do sine of 2 times 0. 2 times 0, of course, is 0. So what's the sine of 0? 0. Then that's going to be times 2 times the sine of another 0, so that's going to be another 0 there, plus, now we do cosine of 2 times 0. Well, 2 times 0, of course, is 0, and cosine of 0 is 1, times cosine of another 0, which is still 1, times 6. And then this is all over cosine of 0, which is 1, times 2. Well, at least we know it's not going to give us 0 over 0 this time. On the top, if I add all those up together, I end up getting a 6. On the bottom, I end up getting a 2. And 6 over 2, of course, equals 3. Which then is our final answer. So for this one, as x is approaching 0, we're approaching a y value of 3.